Hello students, this is Mr. Bornheimer, and for whatever reason today I had a little bit of trouble in recording this presentation in class, so I'm going to go ahead and record it now for you and post it online. So here we go. This is the second part of a three-part series on Unit 1 where we're looking at measurement and reliability, and most of you heard this presentation today in class, but I wanted to kind of touch on some of the highlights, some of the basics. So first of all, today we really covered derived units. And unlike the SI units, which we talked about yesterday, derived units are a little different. Derived units are essentially combinations of SI units or even other units that are not necessarily standard units, and you'll see what I mean in just a second. And we're using our prior knowledge. We're taking information and we're combining it together to create these master units almost. And so you'll see this kind of right here. If you look, you have a Newton, okay? And a Newton is this, what we call derived unit, and we're deriving it from several smaller units like the kilogram, the meter, and the second, as you can see on the screen. There's also joules, and joules are like a Newton, okay? But then you multiply it by a meter, and now you're using a Newton, which is a derived unit, to derive yet another unit. And then there's density, and density is kind of an interesting quantity, and we're going to actually use density next week. Density is kind of neat in the sense that you are taking mass and you're dividing it by volume, and when you compare those two quantities, mass and volume, you get a really unique value, okay? And keep this in mind, especially for next week and especially for your test, density, for your test, hint, hint. Keep this in mind when you're looking at studying, because density is this unique quantity, and it's going to come back time and time again. Okay, so derived units are basically where we take SI units or other units and we put them together to create like a master unit. So kilogram times meters per second squared is a Newton. And if you take a Newton and multiply it by something like newtons represents force, so if you take force and you multiply it by distance, you get joules. And density, if you take mass and divide it by volume, okay, centimeters cubed is a unit of volume, you get density. Okay, so keep those things in mind. All right, now today we talked about measurement reliability and how it's important it is to really look at how reliable our measurements are. In physics, no number stands alone by itself. It usually is tied to some kind of measurement. We've measured this quantity in some way and it's being presented to us and we have to utilize it. Okay, now when we talked in class, I used the example of a remote and how if we were to measure our, let's say the width of my room in a remote, like how wide a remote is, and use that as our standard, I wouldn't be able to give you an answer in millimeters because the remote is the best I can do. The remote, like my remote, which is like right here, okay, is not going to be nearly small enough to really analyze millimeters. So the best I could really do is like a half a remote, maybe. All right. So when we are measuring, our measurements are only as good as the tools we use. And that has to be reflected in the numbers. And so what we're going to actually end up getting into here is which digits in a number, or figures, sometimes they're called both, are significant. Which ones accurately reflect the measurement. Now some of you, and this is perfectly normal, are gonna see me take a number and drop off some numbers on it. And you're gonna think, Mr. Bornheimer, isn't that less precise or less accurate? And the answer to that is no, not necessarily. You have to remember in physics that just because there are more numbers after a decimal point, that doesn't necessarily mean it's a better number. The number is really good if it accurate reflects not only how it was measured, but what it was measuring. And you'll see kind of some examples of that here. Okay, so let's move on. All right, you have two things, accuracy and precision. Okay, accuracy is how closely a measurement is to the true correct value of the quantity. What that means is if I have a correct value, okay, how close my measurement comes to that is how accurate it is. And we can actually analyze that using a percent. Okay, we didn't necessarily do that today in class, but it is possible. All right, so for instance, you know, how accurate is my driving to the actual speed limit? All right, so I might go out and I'll drive 50 miles per hour or 50.1 miles per hour on Telegraph. Well, Telegraph, okay, 24, which is over kind of east of here, west of here, excuse me, the speed limit's 50 miles per hour. So I would say that my measurement or my car is traveling at a very accurate speed. okay? Whereas if I was speeding, that might not be as accurate. Now, precision is slightly different than accuracy. Accuracy is how closely it is to a true value. Precision doesn't really have to do with the true value at all. It actually has to do with how closely a set of measurements. So it actually requires more than one measurement. This is oftentimes why in a lab you'll do 2 or 3 trials. So you can actually analyze. 2 is not good because you might have made a flaw in 1. When you actually try 3 trials on an experiment, you're starting to gather a good pool of data that you can compare against either a true value for accuracy or against each other for flaws, maybe errors in an experiment. And if you find all your values are relatively close, it means you're doing your experiment well, it's very precise, and it's then that you take maybe like an average and compare it to see how accurate your experiment actually was. So accuracy and precision are actually quite important quantities for us as scientists because it really tells us how well our experiments are being run, how well our data is, or how good our data is in comparison to, let's say, an accepted value. Okay, so if you see this chart here, you'll notice here that we have a diagram of 3, you could call them targets, okay? And these should represent probably arrows or darts that are being thrown at the target and where they land. So in this first example, okay, we see that all of the darts or arrows, okay, were kind of randomly dispersed. And that means that they're not accurate because they're not all kind of here near the center. This isn't even really all that accurate. And they're not really precise because they're all spread out. Now here, they're not really accurate, but they are precise because they are grouped closely together. And then there is this target here where they're both accurate and precise. All right, so we see that accuracy and precision do differ, and we can use them here. In your note packet, you should have a really nice diagram of this in the back, and in that diagram, you'll have 4 targets that really display, accuracy, precision, both and neither. Okay, and you're going to want to look at that for your homework tonight. All right, significant figures. This is kind of the bugger. All right, significant figures. You have to remember that it's not about the number and the math when it comes to significant figures. It's about telling us something. See, every number gives us information. It gives us information about not only quantity or units when we apply units, what kind of thing we're measuring, and we talked about that in the first part of this presentation, how we have to have a standard by which to compare. But it tells us a lot about the instrument that was used to make the measurement. Okay, and you'll see what I mean. Okay, the rule of thumb when you're measuring something is that you are permitted 1 guess digit. So if I have a ruler, okay, let's say I have a ruler, and this ruler goes down to, and we'll say it's a metric ruler for ease, let's say it goes down to millimeters. The best I can do is guess halfway between the millimeters. Okay, so if I have my ruler and I'm looking at the millimeters, I can say, well, and something is, I'm really trying to measure it nice and accurate, or I mean very precisely, I would say, okay, maybe it's a 1/2 millimeter. But that's the best I can do. That's my guess because the smallest increment on the ruler is a millimeter. So I can't say that, well, I think that's 1/10 of a millimeter because there aren't little marks that tell me exactly where 1/10 of a millimeter actually is. So the best I can do is a 1/2 millimeter between the 2 millimeter marks. That's what we call the guess digit. And pretty much always, the guess digit is the last significant digit in a number. Okay, so we're going to walk through this a little bit. Here's some examples and some rules. Okay, rules to determine the number of significant digits. First of all, non-zero numbers are significant. So 1, 2, 3 are not 0, therefore they're significant. And the guess digit here would be the 3. It's the last significant digit in this number. Okay, so it's what we call the guess digit. Okay, in this one, zeros are between 2 significant digits. Okay, I like to call these sandwiches. The 0 is between 2 non-zero numbers, 1 and 3. When you have a sandwich like this, where you have zeros in between 2 significant digits, okay, the 0 becomes significant. Now, what I mean by significant, you got to remember, is that I'm actually assessing what these numbers are capable of, or what the instrument is capable of that measured these values. So they're both in centimeters, which means they were probably measured with a ruler. This ruler, according to this, can go to the nearest probably what looks like the nearest tenth of a meter. Okay, because 100 centimeters is a meter. This is a tenth of a meter. This is a centimeter. Okay, so if this is my guess digit, the best I can tell is that it's a meter stick that only has tenths of a meter, and I can guess somewhere in between them. Okay, so this here is telling me something about the device in which I'm using. Okay, and same here. If we move on, we see that final zeros, and the key here, and I want you to underline it in your notes, is the word final zeros. Final zeros after a decimal point are indeed significant. And that means that they have to be at the very end of the number, okay? And they have to be to the right of the decimal. So if I were to take the decimal, the 7 and the 0 in this example off, okay, the 1 and the 0, this 0 would not be a final 0 because it's not after a decimal point. So you have to be careful. Final zeros after a decimal point are significant. So this 0 is. So this has 3 sig figs. This is 3 significant figures. But this one is a 1, 0, 7 sandwich right here. And this 0 is important or significant. Therefore, there are 4 significant figures here. All right, zeros used solely for spacing the decimal are not significant. And if I were you as a student, I'd be looking and say, okay, there's 3 decimal points, or 3, bullet points here. Those bullet points all talk about what is significant. And then there's only one bullet point that talks about what's not significant. So if I'm the kind of person that has a really hard time with significant figures, I'm going to probably focus on the one bullet point that's not significant, and then really just everything else would be significant, kind of like, kind of process of elimination. So I would probably, if I had a problem learning lots and lots of information all at once, or I struggled with learning lots of information all at once, I would try to learn as little as possible that tells me as much as possible. In that case, you want to focus on this bullet point here. Okay? Zeros that are not significant are zeros that are spacers, and both of these examples exemplify this. First of all, the 1, the 8, and the 6 in both examples are indeed significant, according to the first bullet point. There are no sandwiches here, so the second bullet point does not apply. There are no final zeros after a decimal point. These are final zeros, but they're not after a decimal point, so therefore they're not significant. These are not final zeros at all, therefore they're not significant. Because they don't fall into bullet point 1, 2, or 3, they're considered spacing zeros, and therefore they are not significant. Now, this does not mean they're not important. For instance, if I just drop these zeros off, that would drastically change this number. Okay, instead of having 186,000 miles per second, it would be 186 miles per second. And those two numbers are very different. Okay, so we're not talking importance, we're talking significance. We're talking about what does it tell us about the device that measured it. So if I have something that's measuring miles per second, okay, what this measurement tells me is not that it's going 186 miles per second. It is sort of telling me that. What it's actually telling me, what I find significant, is that the device that measured this value can measure only to the nearest 1,000 miles per second. It can't measure 1 mile per second, or even 10 miles per second, or even 100 miles per second. It can only measure 1,000 miles per second. Okay, that's the smallest measurement it can make. Okay? The same thing here with this last value. These all don't mean anything. What this is telling me is that this 186 is important, but that the largest values that it can make are right down here in the, what would be, this is the 1,000th, 10,000th, 100,000th, the millionth category. Okay, so right down here in the millionth, almost to the billionth, okay, we're talking, 10 to the negative 6, 10 to the, right up to almost 10 to the negative 9th. These values are important. There's no final zeros, but these are spacers, and they're not significant. Therefore, there are 3 sig figs here, and there are 3 sig figs here. Okay? All right, now this gets a little tricky, and if you were in class, you would have seen some of the examples of this. During addition and subtraction, your answer should be rounded off to the decimal place value as the measurement with the guessed digit in the largest decimal place. Now that is a mouthful, and we really need to break it down and dissect it. First of all, your answer should be rounded, so you know you're going to have to round something. Second of all, it needs to be rounded to a decimal place. So we have to be good at distinguishing what is a ones decimal place, tens, hundreds, or what about 100th, or 1/10th, or 1,000th. So things that are to the right of the decimal. We have to be able to know our decimal places. Second, we have to know what is the guess digit. And remember, if you remember from one of the first slides in this presentation, that the guess digit is the last significant figure. Okay, so we're looking for numbers that have their last sig fig in the largest decimal place after being rounded. It's a lot to digest, okay? And this is not necessarily the simplest of rules. However, I think you'll be more comfortable with them as we go throughout physics. So let's look at an example. Here we have 100.01 plus 3.0. Okay, now 100.01, its last significant figure is right here, this 1. And this 1 is in the largest decimal place. The largest decimal place that this is in, or this decimal place, is the 100ths spot. This 3.0 has got its last sig fig in the 10th spot. Now, if we had to compare 1/10 or 1/100th, which would be larger? Okay, ask yourself for a moment, which would be larger? If you have a hard time with fractions, think about a pie. If you split a pie up into 100 pieces and take 1, or you split a pie up into 10 pieces and take 1, which piece is larger? The pie that was split into tenths. So the largest decimal place that we're dealing with out of these two numbers, the one that has the sig fig in the last decimal place, that is the largest, is the 3.0. So if we add these up, we get 103.01. However, that being the case, we have to round to the first place after the decimal. So the answer would actually round to 103.0, and that would be the correct value. Okay, I would like you to try this on your own, so go ahead and pause this video. Okay, you should have paused the video. If you didn't, you should have really paused it. Before I'm about to tell you the answer, I want you to let you know that you should just add these two numbers, and it comes out to 64,541 centimeters. However, the value that has the last sig fig in the largest decimal place is going to be this 64,300. And when you round it, you have to round to the hundredths place because that is what the rule states. So the answer is actually going to be 64,500. Okay, and the final answer will have 3 significant figures. All right, now multiplication and division, much easier, much easier. First of all, you don't have to worry about decimal places, and we'll just go ahead and dive in. Okay, when you are discerning how many sig figs your answer should have in multiplication and division scenarios, all you have to do is just multiply the numbers. Okay, so in this case, you end up with 88 meters squared. Then you say, okay, the numbers that I started with, how many sig figs did they have? The 44 had 2. The 2 had 1. You always pick the smallest number of sig figs and round your answer to that. So 88 meters squared rounded to 1 sig fig. Okay, what do you think? 88, you'd have to round up to 1 sig fig, so it would be 90 meters squared. That would be the correct answer. However, if you wanted it to be 88, you didn't want it to be 90, and that confuses you a little bit. You could change this problem so that instead of 44 times 2, you'd have 44 times 2.0. Now, believe it or not, it does change the answer. Because the 44, okay, right here, is being multiplied by something that's 2.0, has 2 significant figures, your answer can have 2 significant figures, and therefore 88 meters squared would be the appropriate answer. So it does matter. 2 and 2.0 are very, very different numbers, and you have to be aware of that when you're working in physics. All right, rules for rounding numbers. For our purposes, we are not going to do these particular sides, and you're not going to be responsible for that information. When you're rounding using sig fig rules, the rounding rules change a little bit from what you probably learned in grade school. If you were in AP Physics, we would definitely go over these, but because this is general physics, we're going to just go ahead and skip over these slides, so I'm going to go ahead and just skip through them here real quick. We are going to move on to percent error. All right, percent error. This is pretty straightforward. Okay, basically, anytime you are doing an experiment, you're comparing your results, your values that you find in an experiment against the real value. So anytime we compare our values against a true value, we're looking for accuracy. Again, that word accuracy comes back. Okay, so what we're doing here is we would look up a real value, so a literature value. There are places to look these up. The internet's a great resource. Okay, and what you would do is you'd look up the actual value and you would take your value and compare. So you would take the absolute value of your value minus the real value divided by the real value. Now this would usually give you a decimal. Most times the decimal is right around 1 or less than 1. And when you multiply it by 100, it turns it into a percent. Okay? I wrote it two ways because sometimes this whole literature thing gets people confused. Sometimes, as a teacher in a lab, we'll give you the value that is considered to be the standard. So you would take your experimental value and you would compare it to the given value, the value we gave you, and you would say, okay, how accurate is my answer? So you would take your value, subtract the value that you were given or is considered to be the correct value, divide by the correct value or the given value, and multiply by 100. One of the things I want to emphasize here, and we might, not necessarily talk about it in class, is that there is really no wrong data in an experiment. If your values are off from a given value, that's just as pertinent and just as important as if your value is right spot on. And the reason is that experiments tell us information. An experiment that's got a large percent error tells us that a lot about, oh, hey, maybe this didn't work or that didn't work or this is not a good way to do something. And that's just as valuable as getting the given value, sometimes even more so. Okay, so just because you end up with large percent errors does not necessarily mean that what you did in the experiment is not good or bad. And you'll find that when we do labs and stuff, if you end up with large percent errors, we calculate it. That doesn't necessarily mean you did bad on the lab. People who could get 0% error are more likely to get marked down than people who have a percent error. Okay, so here's an example, and you should work this out on your own. This will be the last slide that we discuss in this presentation, and just to kind of show you how the values would be plugged into the equation for percent error. Here this reads, determine the percent error for the density of aluminum found experimentally. Okay, so found experimentally to be equal to 2.60 grams per centimeter cubed. Notice, a couple things come into play here. First of all, these are the units for density. So density. It's a derived unit, grams per centimeter cubed. The number here has 3 significant figures. This 0 is significant because, it is a final 0 after the decimal point. Notice that our given value, actual density, is 2.70 grams per centimeter cubed. It is important that when you compare things like these two numbers, that the units be exactly the same. So in this case, grams per centimeter cubed, grams per centimeter cubed. If that's the case, we can go ahead and compare. And the reason that units have to be the same is because just like if you were to subtract two algebraic things with, you can't subtract x squared and x. Okay, the units are almost treated like variables. They have to be the same if we're going to subtract them. And then they cancel out beautifully when you subtract them and then divide. And that's great because percents don't have units. Okay, so we want our units to cancel out. And you'll see more of that tomorrow's presentation with dimensional analysis. Okay, this is the example problem. Go ahead and figure it out, and we'll talk about the answer in class. I thank you for watching, and I hope you have a good night.